Hello. This experiment on the paper chromatography of amino acids will present another facet of the chromatography of water-soluble materials. Today we will try to chromatograph amino acids using a butanol acetic acid water solution in order to show their separation in experimental conditions. We'll start off by using visible dye materials in order to demonstrate some of the points of paper chromatography. Firstly, there's a matter of spot size and its effect upon paper, the separation of the colored materials. If we start with a mixture of dyes that is sold commercially as Scripps washable black ink, we can show the effects in very visible fashion that require reagents to develop under conditions of chromatography of the amino acids, which are not colored. Now, the general idea here is that if we make a very small spot and then succeedingly larger spots, upon the paper, that ought to do it, we can see the effects upon the chromatography as the solution, as the paper spots develop. We'll use a mason jar as a chromatography vessel. It has a cover which has been modified by adding a hole and a little hook made out of a piece of paper clip, and we'll use distilled water as the developing agent. And you will see that Scripps washable black ink, as many colored materials, as typical of many colored materials, is composed of a number of dyes. As we put this in, the colors will develop as the liquid rises through the spots and goes on up, and you will see the effect here of the size of the spot upon the resolution of the colors as they develop. Now here I will place a chromatogram which has been developed already, and can you set? This chromatogram was developed yesterday, and you see that there are red, yellow, and blue dyes in the Scripps washable black ink. Now, each ink, I would imagine, probably has a different composition of dyes depending upon the manufacturer, but this one is a rather good test material. And you can see in the chromatogram that was developed the dyes, and you see that the paper has been overloaded. Paper shows the effects of adsorption of the dyes, in that the red dye tends to trail badly, partly because it is overloaded and the paper cannot handle that much, adsorb that much ink or dissolve it in its bound water. The green and blue dyes, yellow and blue dyes, travel pretty much with the front, so that this is not a terribly good example of separation. In order to use this for quantitative or even qualitative, good qualitative separation, one would select the liquid to eliminate some of that trailing and some of that adsorption, and also to slow down the movement. However, it shows you the effects, and if we can go to this one, you see that the separations are somewhat better with the very small spot on this side of the screen. There is a very small spot which is separating very much better than the largest one on the other side over here, where the colors are trailing into one another very badly. This then demonstrates the great effect of spot size and quantity of material added to the paper relative to the ability of the paper to hold the dye and to transport it properly through the solvent system. All right, the next matter would be then the visualization of the spots once they have been developed in the case of water white materials or uncolored materials. And so here we have a piece of paper on which we have made X's and labeled the various amino acids that are to be spotted upon it. All right, we will put this paper on a clean surface, and then using a capillary pipette, spot, for instance, some aspartic acid on the spot labeled ASP for aspartic acid. Now here we're just testing the color development procedure, and there is no need to keep the spots small. We want to be able to visualize them. All right, after the paper has dried, and we'll put it near the hot plate for a moment to let it dry, or in better, we'll take a piece of paper which has gone through this treatment, and each of the amino acids mentioned in the experiment have been dried upon the spot, and we will develop this first in ninhydrin by putting it into a solution of ninhydrin dissolved in acetone. This then will dry rapidly. Then we can put it over the hot plate. And in order for you to see it, I think perhaps it would be better for me to move the paper around here. All right, as that color comes up, you should see this set of spots developing. Now you see there, can you get both of them in, please? You see there are purple spots representing glutamic acid, leucine, valine, aspartic acid. Tyrosine gives more of a brownish spot. Proline gives a yellow spot, and you see them developing over here. These are the ones that I just spotted. We seem to have a shadow. All right, the proline gives a yellow color, tyrosine gives a browner spot, and the other amino acids give varying shades of purple. Proline alone among the naturally occurring amino acids, proline and hydroxyproline, give a yellow spot because of the difference in their structure from the alpha amino acids. Their amino group is bound up in a ring structure. All right, this then shows that group. If we do the same thing and develop using isoton, and this requires a little bit more heat. I'll put it down closer. You'll see these colors come up. And here you have the blue color that the forceps is on for proline, and the rest of the amino acids give either very faint blue colors or no color, and this then is typical of the isoton colors. So proline, which in very small quantity would give you a faint yellow color with an anhydrin, possibly be missed, can be brought out more effectively with isoton. As you see here, the colors are coming out. There's the proline color and a little bit of color from some of the others, but this test is almost specific for proline and hydroxyproline. All right, with those color reagent, location reagents, then we can proceed to the preparation of amino acid chromatograms for identification of amino acids. Now on a piece of, let's step back just a moment to this chromatography, and you see the colors have developed just as they did in the sample chromatogram that was shown to you earlier, and we can take that out, let it dry. And then these materials can be examined either by spot color reagents or by measuring the distances, as we will do presently, to get the RF values for the various amino acids. Let's go back to the amino acids then. Here we have the same piece of paper. It has been marked with abbreviations for aspartic acid, glutamic acid, one for an unknown as called for in the experiment, tyrosine, valine, second unknown, phenylalanine, and leucine. We then, just as with round pieces of paper, in order to identify the amino acids, now we make very small spots, like so, of each of the amino acids called for and of the unknown that was called for in the experiment. We then put that piece of paper, after the spots have thoroughly dried, into another jar in which butanol acetic acid water has been poured. Hang the paper on the hook, put it in the jar, and again we let the reagent by capillary action move up through the origin of the spots, and then it washes each amino acid along as the reagent moves upward. As the butanol acetic acid moves upward, it passes through a spot and the material dissolves in the butanol acetic acid, travels upward a little bit until it finds a region of paper where there is no butanol acetic, where there is no amino acid, and it redissolves back in the water that is bound in the paper. And this process is repeated an infinite number of times as it travels up the paper. Eventually we stop the chromatogram when the butanol acetic acid water mixture has migrated upward for a considerable distance, and we have such a chromatogram here that has been developed by the same process. All right, this one we will develop with an anhydrin. And we will let it develop over the over the hot plate. Perhaps come up a little bit so it won't get overheated. And those colors will come out, and we will get a chromatogram that looks like this. Now, the amino acids spotted on here were, from this side, aspartic acid, glutamic acid, the unknown, and then tyrosine, valine, the second unknown, and then phenylalanine and leucine. Now you see the second unknown here has moved the same distance as the leucine, and therefore it must be leucine, assuming that it is not some completely unrelated material. The first unknown here moved the same distance as the phenylalanine, and therefore it must be phenylalanine. And you can see the spots coming up on the paper. Actually, when they first come up like this, you can sometimes get additional information from the color as it comes up. You see the aspartic acid is a little bit lighter blue. The tyrosine is browner. Glutamic acid is more purple. And these are more lighter lavender color. Now, this then serves to identify unknown amino acids if you have the exact amino acid handy to serve as a reference. On the other hand, if you have to go to the literature to search out a value, you need a yardstick for measuring. You have the ruler, please. Down there. If we take the distance that the solvent front moved, and that is right up here, we can find then that the point of origin to that point is 9.3 centimeters. So the front then moved 9.3 centimeters. If we take the middle of the spot and measure the distance it traveled, then the leucine traveled 6.4 centimeters. So we have 6.4 over 9.4, and that will be roughly 0.60. And so the RF of that material then, the leucine, the known material, is 0.60. We can set up a ratio for each of the amino acids then, measuring the distance that that particular amino acid moved, center of origin to center of spot, versus the distance that or over the distance that the front moved. We get a ratio called the RF of the distance that the spot moved to the distance the front moved, and that is relatively unique to the individual amino acid. It is not unique because it cannot be measured that accurately. It varies slightly with the conditions. If the butanol acetic acid water is made up with somewhat more water or somewhat more acid, it will change. If we use a different eluting solution, developing solution, the buffers, the amino acids will move differently. But for a single reagent, a single amino acid, that number will remain fairly constant and can be used as a rough identifier. Now, if we take, for instance, the RF value of a particular amino acid in butanol acetic acid water, and then perhaps in a butanol pyridine solution, and then again in phenol and water, a number of developing reagents. And if we come up with the RF value, a constant, if an unknown and a known material have the same RF value in 3 or more solvents, then this is very good evidence that the compound is identical, because if you explore a range, if you use the butanol acetic acid, for instance, which will suppress the ionization of the hydroxyl ion, of the carboxylic ions, if you use butanol ammonia, which will suppress the ionization of the basic groups, use phenol, which gives it an entirely different solubility characteristic, then there will be very few compounds which will have identical mobilities in all 3 of these materials, and this is very good presumptive evidence for the identification of a compound. Thank you.